Today I'm going to talk about my graduate work at Michigan State University. I was able to work on producing scandium-47 through isotope harvesting for medical applications. I'd like to start talking about the facility where I was able to do this work. It's called the National Superconducting Cyclotron Laboratory. There are two superconducting cyclotrons here in green, and they accelerate a stable ion beam that's anywhere from oxygen all the way up to uranium, up to about half the speed of light. This allows for fragmentation reactions to occur, and exotic fragments then get separated out and sent on to the many beam stops or end stations that you see in this picture. Today we're going to talk about the leftover primary beam that goes unreacted and doesn't result in a fragmentation reaction. So if we zoom in on the fragment separator here, this involves a beam blocker, which right now is a solid metal block that's placed after the first dipole magnet in this separator. It collects all of the leftover primary beam, and the products decay in this stable metal block. We would like to use that kind of leftover primary beam to produce interesting isotopes for applications like nuclear medicine. And so this is called isotope harvesting. This is a schematic of what this could look like at the National Superconducting Cyclotron Laboratory, where more than 90% of the primary beam remains unreacted. And so we would like to put a flowing water target here to collect that accelerated primary beam and induce nuclear reactions in that water matrix. The flowing water then moves all the products from the target onto a water system where they can be collected for offline use in other experiments. So during my time at Michigan State, I was able to test the durability of the target that we are using for this work and help in designing the water system. And then I was also able to help with collection methods, like collecting the aqueous ions out of this system, and then performing chemistry on those products. And today I'm going to be mainly talking about these second two aspects of the project. So let's zoom in on a specific example of a product we can make through isotope harvesting that we're interested in for nuclear medicine applications. So when the calcium-48 beam is run at the National Superconducting Cyclotron Laboratory, we create a significant amount of calcium-47. This is the parent to scandium-47, which is interesting for nuclear medicine. So here I'm showing a preclinical study that was done with scandium-47. In this image down here, we have scandium-47 bound to DOTA, and this complex is connected to folate, which is a molecule that targets folate receptors on the surface of certain cancer cells. So in this experiment, they were able to demonstrate the diagnostic and therapeutic applications with scandium-47. So scandium-47 emits low energy gamma ray that can be imaged with SPECT imaging. And you can see that in this figure here, where the tumor is indicated by these green arrows, and the mice that were studied are clearly visible. They also compared the lifetime of control animals that were not given a dose and test animals that were given a dose of this radiopharmaceutical to demonstrate the significantly longer lifetime of the animals that were treated. And this treatment is done through a beta minus particle that's emitted from scandium-47. In these experiments, we were able to measure the production rate of calcium-47 at the NSCL. We measured almost a 2% beam conversion rate, which is quite high. So this is reported in percent of beam particles that irradiate the target that are converted to calcium-47. So we use this measurement to kind of predict how much calcium-47 we could produce in a standard experiment where our beam blocker could be in place collecting all the unused primary beam. And so you can see that in this graph here, where at the end of a 120-hour experiment, we have a significant amount of calcium-47. It's approaching 110 millicuries, and this would be plenty of activity for us to conduct future preclinical studies. I have this comparison here that you typically use less than half a millicurie per mouse, and so this would be a significant research quantity of scandium-47. So I'd like to show different aspects of the harvesting system that we developed in this work. So this is just a schematic overview where we can look at the main sections. So we have this water conditioning and monitoring loop, which has different sensors and meters to monitor the water. And it also helps us to condition the water by breaking down peroxide and releasing heat from the water. This system pumps water through the target at about 15 liters per minute and has a large, about 50-liter water reservoir. And then we have a couple of side loops that allow us to collect the radionuclidic products produced in the target. So this first one in yellow is the aqueous chemistry box, which collects ionic aqueous ions. And then we have this gaseous box, which also can collect radionuclides that are in a gas phase. So this image shows a cross-section of the isotope harvesting target that we have used. In the left, you can see the water entering our target and passing through this narrow pathway. This allows for very rapid flow for good cooling of the front face of our target. And then that water flows out of our target and onto the rest of the system, carrying the products with it for collection. This image shows the main part of our isotope harvesting system. You can see in this secondary containment that we have a number of pieces of equipment. Here you can see the water reservoir is this black tank. The pump that pumps water through our whole system is sitting down here on the floor of the box. And all the electronics that controls and monitors this system also sit here with this box. So now you can see the pictures of the boxes that are used for collection. On the left-hand side is the aqueous chemistry box. At the bottom here, we have a lead wall. Behind that is additional shielding that allows us to handle the high activities and transport it with shielding that comes with it. And then inside this the shielding is a small cation exchange resin that allows us to collect any cations from the water, including our calcium-47. So that's what I'm showing here on this left-hand side. In our water system, we collect the cations on this, this cation exchange resin. We then take that resin to our lab and we rinse it with acids like nitric or hydrochloric acid to get as much of the calcium-47 that we can off the column. Now this is a mixture of many different cations, and so then we prepare the solution to go into our purification process. Down here in this table, I'm showing that we perform 3 irradiations with the calcium-48 beam to optimize these, each of these steps in our process. You can see that both our collection efficiency, collecting it from the large amount of water in our system, and then recovery off of that cation exchange resin were high for all 3 experiments. They were greater than 80%. So then we take that cationic mixture of our products that includes our calcium-47, and we use a second cation exchange resin with a hydrochloric acid gradient in order to separate out just our calcium-47. You can see that gradient here on this graph across the top, and you can see that we're able to elute isotopes of sodium, magnesium, potassium, and beryllium before we finally elute our calcium-47 in a very clean fraction. You can see that our total separation yield was high at 97% of our calcium-47, and we also had a very high purity of that calcium. And then if you look at our process from how much calcium-47 we produce in our isotope harvesting system, all the way through to the amount of calcium-47 in this purified fraction, we're looking at about an 80% recovery yield. After we have our purified calcium-47 fraction, the next step is to wait for scandium-47 to be generated in the solution, and then we need to purify the scandium-47 for our applications. So this process that we used was published by Dominique et al. In 2017, and we used this process for our purposes in isotope harvesting. So we start with our calcium-47 in 4 molar HCl, and we pass it through a DGA resin, which is an extraction chromatography resin. It allows our calcium to pass through the resin, and our scandium-47 remains here on the resin. So then to get the scandium off, we rinse with a lower molarity of HCl, and we have our purified scandium-47 in this fraction. However, at this point, it's in about 7 to 10 milliliters, which is too high of a volume to have high radiolabeling yields, which is our ultimate goal. And so we do a second step, which concentrates the scandium-47. So much the same way as the first step, we use a DGA resin. In this case, it's significantly smaller, which allows us to really do that concentration step. So we put the 3 molar HCl containing scandium-47 back on a small DGA resin and rinse it off in low acidity dilution step. And it's this small, less than 1 milliliter fraction of purified scandium-47 that we then use for radiolabeling. And I've demonstrated the radiolabeling here schematically, where we really want our scandium-47 in this case to bind to DTPA, which is a chelator that is bound to TOC. And TOC is a biomolecule that interacts with neuroendocrine tumors. So this would allow us to use scandium-47 in a targeted internal radiotherapy experiment. So we can look at the results from using this generator procedure. In the 3 experiments, or the 3 generator steps that I'm showing here, we performed successive generators, which means we had a purified calcium-47 fraction that we used multiple times, milking it to get the scandium-47 out. And for these, our goal really is to have the highest amount of activity in the smallest volume to give us the best radiolabeling results. So you can see in this table that our recovery after that first purification step was quite high for each of the generator runs. For the second concentration step, we have a bit smaller of a recovery yield, and this is because we really need to keep the volume as small as we can. And you can see that in this elution curve, that off of that concentration column, we have a tailing behavior in our elution. And so we take about 700 microliters, and we normally get about 70 to 80% of the activity in that small volume. So we then take that fraction and use it for radiolabeling. We essentially add DTPA TOC to the solution and heat gently to encourage interactions. And so we performed radiolabeling for each of the 3 generator runs that I was just talking about. And you can see here that we had a very high radiolabeling yield of greater than 95%. And this essentially means that we had greater than 95% of the scandium-47 we added into this mixture, chelating and bound to that targeting agent that I was talking about, DTPA TOC. And you can visualize that here in this quality control step that we ran. This is basically a separation method that allows us to separate scandium-47 that's still free in our solution from the scandium-47 that's bound to our chelator. And so you can see here on the left, we have a control spot of free scandium-47 that moves about halfway up the plate. And in our radiolabeling solution, we only really see this one spot at the bottom, which corresponds to our radiolabeled activity. And you really don't see any free scandium moved up to the middle of the plate. And so this really demonstrates our high radiolabeling efficiency and our ability to use this scandium-47 for medical applications. So in conclusion, we were able to successfully develop and integrate these methods for specifically isotope harvesting produced calcium-47. And we're able to demonstrate that we can reproducibly use this source to radiolabel a medically relevant biomolecule. So really the next steps are transitioning this project to the next generation linear accelerator called FRIB that's currently being commissioned at Michigan State. And so I'm sure that these methods will need to be adapted for the true conditions that will show up at FRIB in these experiments. And based on these results, I think one of the most challenging things will be the purification step to make sure that there are no competing ions for the radiolabeling. And this is all really for the goal of having a regular scandium-47 supply at FRIB for preclinical research in the future. And at FRIB, they're going to be using 400 times the beam power as we were using at the NSCL. And so this can produce a very large amount of calcium-47. Here you can see that we estimate in a 24-hour irradiation greater than 14 curies of calcium-47 being produced at FRIB. And with that, I would like to thank all the members of my group, which they helped me through each of these experiments, especially Greg Severn, my advisor, for being so supportive and encouraging, and Kathy Domnanich, who was our postdoc during these experiments. And I'd like to thank funding through the SSGF program and also through the DOE Isotope program. Thank you.